Yes, thank you. Thank you for organizing this. I think it's been great to have these like year or so, and thanks for the invitation. So I'm going to talk about some recent work that I've been doing, and I've been thinking about basically how do you regularize the factorization method in an analytically kind of rigorous way. And so this is partially funded by the NSF, and I think what we're going to do is just going to jump right into it. So this first kind of section of the talk, we're going to just kind of introduce the problem that we're looking at. For the audience at hand, some of this that we'll talk about is a little redundant, but for the YouTube audience, maybe they're not as up to date on some of these things. And so we're going to talk about how to solve inverse boundary value problems with this kind of regularized factorization method. And so the idea here, right, like many of the people in the audience know, this kind of inverse boundary value problem, you can think of it as, most inverse problems are something like, an input physical model to output. Here, the input's going to be some kind of boundary condition, some boundary data. The physical model is a PDE. And the output are the values of the solution, right? So, it could be, in this case, we'll see what we mean by values of the solution, we mean the values of the normal derivative. But you can think of other kind of values of the solution that you can probably measure for some inverse boundary value problems. And so the forward problem that you solved in your kind of PDE courses was, you're given the boundary condition, you're given the PDE you want to solve, and you're asked, compute the solution to the wave equation or find a temperature profile or some of these things. But the inverse problem is that you have the input and output, right? So you can prescribe the input that you want, and you can measure the response physically. And you want the model, right? There's some information about the physical model that is unknown to you that you want to recover from the input and outputs, right? And so one of the ways we're going to try to do this, we're going to try to solve an inverse shape problem. And one of the ways we're going to try to do this is using a qualitative method. So the idea here is you have this red subregion in this square. So the outside region of the square is known, but this interior region that's in red, unknown, and you want to recover it from your measurements. And what we're going to do is, for a qualitative method, right, we're going to use the full nonlinear model, okay? The solution to the PDE definitely depends non-linearly on the coefficients and things in the PDE, all right? So the underlying model is non-linear. If you're trying to recover things like coefficients or regions of interest inside, that depends non-linearly. The solution depends non-linearly on that, even if the PDE itself is linear. What you want to do is you want to try to recover these with little a priori information. So I don't want to know a lot of information about the region of interest. And the way I'm going to do that is by constructing a function W that has this kind of indicator function property, that it will be positive inside the region of interest and will be 0 outside the region of interest, okay? And we're going to compute this function W. We're going to compute it using that fully nonlinear model. So it won't be any linearization or anything, but we will be able to get this function W from the data that we have. And we want to do this in a way that's computationally fairly simple and analytically rigorous. And so, like, once again, most people in the audience probably don't need this, but we want to do this because we don't need a lot of a priori information. So just think about finding the root of this very simple equation, right? There's one answer, it's 0. And if you just naively, like I did here, try Newton's method and an initial guess of 3. So depending on how good your resolution is on your screen, you may be able to see that 3 is here where my cursor is. And that's well outside of that hump there. And so the way Newton's method would work, linearizing, solving the equation for the tangent line equals 0, and then updating, that's going to diverge for any initial guess that's outside of these kind of 2 humps, or this hump and valley. So you need an initial guess that's in between, here this is like 2.5, 1.5, and negative 1.5, let's say. So you need an initial guess in this interval, and then Newton's method will work great. So you need some a priori information, right? You need to know what interval you should be looking for the solution, basically. So, how does that relate to this inverse boundary value problem that we're going to study? Well, most iterative methods, they need a good initial guess to ensure that you're going to converge to the right answer, right? That basically means there's some a priori information that you have to assume that you know, right? Just like in the problem that I discussed earlier, you knew, right, to get the right answer, you have to know the interval where the root is, right, to kind of find it. And so for an inverse boundary value problem, that could mean a lot of things, right? For an inverse shape problem, you could have to know the number of objects that you want to recover. If there are two objects, but your initial guess is only for one object, that might not converge. If depending on the, kind of physical conditions or parameters in a problem, you kind of have to model those and add those into your solver. So you need a guess for those, right? And that's just a lot of information that you may not have on hand. And so what we'll see here is that qualitative methods will allow us to solve the inverse shape problem with little a priori information. But there's always a cost to pay, right? I like this quote here. Basically, kind of what this says is, even though, there's nothing you can do for a lack of information. So qualitative methods, even though I like them very much, they do require a lot of data. You got to take a lot of measurements in order to get them to work, right? So there's nothing you can really do mathematically. If you're going to just, assume that you don't have any of this a priori information, you just physically have to collect more data to get this to work, is what that says. Right? And so even though the problem I'm going to talk about is from diffuse optical tomography, basically, I like this picture here from somebody's website that explains electrical impedance tomography. And so what we're going to do here, think of, you have some kind of boundary measurements from these electrodes, and you want to get an image like this here, right? And so the way these kind of qualitative methods work is that you get these images here. Maybe for us, we won't really actually know the value of the function here, but if you get images like this, you can tell, okay, that lung is a lot smaller than the other one. So maybe that, that's where the issue is in the patient. And that could be, in many cases, good enough, just to detect where a defect is, right? So the problem that we're going to consider here comes from, like I said, this is kind of modeled from the diffuse optical tomography. So you have this boundary value problem for a solution U in H1 with some given boundary data F. And so the region D0 is contained inside the region D. So you're trying to recover, right? What we're going to try to do is recover this region D0, where this is just the chi is the indicator function. So it's 1 if you're in the annular region, D minus D0, or 1 if you're inside of the region D0. So you can easily check that this is a nice, well-posed problem. So you have this nice, unique solution in H1 to this problem. And just like in the electrical impedance tomography case, we assume that the outside region D is known. So if you go back to the picture I showed a lot earlier, you had that square, right? The square is known, but the inside region in red, that's unknown. But since the square is known, then you can always find the harmonic lifting for the data F that you prescribed from the boundary. So what we're going to try to do here is recover just region D0 that is totally contained in D. By totally contained, I'm actually assuming that the distance between the region D and the boundary, the distance between the region D0 and the boundary of D is positive. There's some positive distance between, they're well separated. And we're gonna try with the, assuming that we know these Dirichlet and Neumann maps. So lambda takes F and maps it to the normal derivative of U that solves 1. And I'll refer to this as lambda 0, takes F and maps it to the normal derivative of the harmonic lifting. Right, so that's the problem, that's a setup. We're going to try to run through some qualitative methods to solve this and see, why one wants to regularize the factorization method and how one does this. right?
Could I
And
ask
so,
a question about the problem
yes.
so that I understand what you're trying to solve? What does it mean you want to reconstruct the support of the inclusion?
So you want to recover D, the region D.
What about it? The shape
The
or?
shape, the shape. So you want images like, let's say this here, where if this is the box here, I want to compute this function
Oh, I
W
see.
so that I get like this red picture here. You see, specifically, this is the region of interest.
I see. So in other words, you want to find the closure of that region.
Yeah.
Okay. Okay, I get it.
Yeah. All right, so yeah, let's run through some qualitative methods for this. And so here are just some manuscripts. This is a good one for the factorization method in general. They go through this for a few different models, EIT, scattering, electromagnetic scattering. And they also, even though here I'm talking about an elliptic inverse boundary value problem, these methods have been extended to time domain problems as well. And that's also quite complicated, but you have some manuscripts that talk about that. And so, this list by no means is extensive at all, but just some of the ones that I know of and that I've read and know very well. So, I said this, regularization for the factorization method. So guess what? We're going to have to factorize our Dirichlet and Neumann map. Surprise, surprise. So what I'm going to do is define a function W that solves this source problem here, right? For any H and L2 of the interior region, right? It's a well-posed problem. So I can always define the source to Neumann operator. So G will map H to the normal derivative of W. And you say, well, why do we care about that function W? Well, actually, this W here will equal the difference of our Dirichlet and Neumann maps applied to F, provided that H is negative U in the interior, okay? And that can easily just be seen by if you subtract the equations for U and the harmonic lifting, they solve exactly equation 2 with the H being negative U. It's not hard to see that. And the well-posedness is why these have to be equal for every F. And so you say, okay, well, I can then just define the solution operator. We know that this equation 1 is well-posed. So define the operator that takes the Dirichlet data to the value of the function on the interior. And there you go. So what we can do now is factorize our Dirichlet and Neumann map this way. So S maps you to U on the interior region, and then G will take negative S and map that to the normal derivative of W. Okay. So that's our initial factorization. And one of the reasons we want to do this is obviously the Dirichlet and Neumann map here depends on the region of interest, but it's a very implicit way it depends on it. But G and S depend on the region of interest in a very explicit way, right? The range space for S is L2 on the interior region, right? The domain space for G is L2 on the interior region. So these actually, the dependence on the region D0 is way better understood than it is for this here. And we'll see that that's going to be helpful later on. And so we have these operators, we can analyze them. And you can show that the adjoint of S, which will map L2 into H minus 1/2, has to map G, which is the source for this new problem, and map to the negative normal derivative of V, right? And this is done, you use the fundamental theorem of applied mathematics, right? You integrate by parts to make sure everything works out. And you can show that for this function V, that's the correct adjoint for S. And the operator S is compact and injective, right? Compactness, just L2 is H1 is compactly embedded in L2. And the injectivity comes from a unique continuation argument. You can also show, remember, like I said, the operators G and S, they have a really strong dependence on the region of interest. So you can show that G has to satisfy this, that the normal derivative of the Green's function will be in the range of G if and only if, right, the singularity is inside of the region of interest. And the way this works, if you remember the equation for G, right, you defined it by that W. And that W is harmonic in the angular region. So D minus D0. And so by Holmgreen's theorem, if this were in the range of G for your sampling point not being in D0, well, you'd have a harmonic function that would have to equal the Green's function everywhere except for the sampling point Z. And that's problematic. The Green's function obviously is unbounded there, but W would be analytic there. So that can't be true. And so if Z is inside the region of interest, well, you just have to construct a function W that satisfies the properties that you need, and that's not that difficult. Okay. And so here now, because of our factorization, we know that our data operator here is compact, injective, and we can show it has a dense range. So the compactness just comes from our factorization and the fact that S is compact. Quite simple there. What about the injectivity and the denseness of range? So let's look at this here. This is equality that we have, where these brackets just are the L2 inner product on the boundary delta D. And so either if F is in the null space of our operator, then the left-hand side is 0. Or if F is perpendicular to the range, then the left-hand side is 0. Okay? So for either case, for injectivity or denseness of range, give me an F that's in either the null space or perpendicular to the range. The left-hand side is 0, but the right-hand side has to be strictly positive. It's strictly positive due to the fact that harmonic functions minimize the Dirichlet energy. So that's non-negative. And this has to strictly be positive due to a unique continuation argument. So there can be no F that would make this left-hand side 0 due to the fact that the right-hand side is strictly positive. So now we can do some analysis here. So since we have a dense range for our operator, I can always construct a sequence that does this, that approximates the normal derivative of the Green's function for any Z in the region that I like. And so now what if this approximating sequence had a bounded norm as epsilon goes to 0? Well, we're in a Hilbert space, so it's weakly convergent. That weak convergence turns to strong convergence since it's a compact operator. And since limits are unique, this would have to actually equal the normal derivative of the Green's function. So that says the normal derivative of the Green's function would be in the range of our Dirichlet and Neumann map. That's going to be problematic due to the fact that the range of this operator is contained in the range of G. So many of you may know that this is basically the linear sampling method. You try to find a nearby solution to this equation. So this equals Green's function. And you check the norm of the solution, right? We now have that the norm of the solution has to become unbounded if you're not in the region of interest. Okay? And so that's what linear sampling method is. And the way you reconstruct things using the linear sampling method, you choose some grid points in the region that you know. You solve this however you like. You're going to need some regularization technique, but you can solve this problem. And then the W would just be the inverse of the norm for that solution here. Okay, and you can reconstruct, if you want to reconstruct the boundary of the region, you can just take a level curve, right, where this is approximately 0. And so here's, one of the pitfalls for the linear sampling method is nothing that I said guarantees that this is going to be bounded inside the region of interest. Right? Outside the region of interest, this is definitely unbounded. I did not say it was bounded inside the region of interest. So that's a big theoretical flaw. And one way to fix that is with the factorization method. So we need to work a little bit harder. The factorization method doesn't just need that kind of factorization that we have for the linear sampling. It needs a symmetric factorization that looks something like this. And we'll define what this operator T here is in this slide. So you need this, right, for the factorization method, you need this kind of symmetric factorization to get things to work out. And so what you can do here is if you just take equation 2 for W, right, which is exactly this, but I added W on the interior region to both sides, right? And then you say, okay, well, G we know maps H, right, the source to the normal derivative, but also S star also is a source to normal derivative operator. It maps the source. If this were called G, it would map the source G to the normal derivative of this solution. So if this was our G that we use to define our operator S star, then this equality would hold. And so now I can just define another solution operator T that will take the source and map it to the source plus the solution W on that interior region. And so then that just says that G is, negative S star T. And if G is negative S star T, well, we have our symmetric factorization for our Dirichlet-Neumann map, which is exactly what we need for the factorization method to work. And so one other thing you need for the factorization to work is a coercivity type property for the middle operator, okay? And you can show that for the operator T here, that is actually strictly coercive on all of L2. And that's a simple integration, use the PDE and integrate by parts argument. The inner product of TH and H is by definition this. And then if you use equation 2, which basically says that the indicator function times H is equal to the Laplacian of W everywhere in D, you get this here. And then you just use Green's first theorem, and there's no boundary term because W has a 0 Dirichlet condition. So this, for sure, tells me that T is coercive on all of L2. And we can also connect the range of S star to the region D0. And one way you can do that is if you just notice that the normal derivative of the Green's function is in the range of S star if and only if, again, Z, the sampling point here, is inside of the region of interest. So the way you do that is, these ranges are equal. We have this factorization and T is invertible. So fairly simple argument there. All right. And so here is the theorem for the factorization method. It would take more than one slide to kind of see what's happening, unlike the linear sampling method. But the idea, very quickly, is this operator is a positive operator, so it has a square root. You can show that the square root of this operator, its range is equal to the range of S star. So then the range of the square root now knows where the region D0 is. And you can use Picard's criteria to explicitly say when something is in the range of a compact operator. And so this here is what that is. And so basically you have to use the singular values and singular vectors of this operator. So you have to go from the square root back to the operator, but you can easily show, that this sum will be finite if and only if the sampling point is in the region of interest, where you're using the singular values and singular vectors of the data operator here. So lambda are the singular values, not the eigenvalue, singular values, and x's, those are the right singular vectors. And so for the factorization method, that's great. This is now if and only if. This quantity, which I can compute specifically from knowing the Dirichlet-Neumann map, can recover the region of interest, okay? And so how do you do it? How do you solve the problem? Well, choose some grid points in D, you compute this sum, and if you want, let's say the boundary, you can just plot the contour plot of this, or if you wanted the boundary, you can plot a level curve close to 0, and there you go. So here's the problem. The eigenvalues, the singular values are going to decay fairly rapidly, especially if the exterior boundary is smooth. Then some elliptic regularity arguments are going to say that that operator is compact. Well, the operator is compact, but it's going to be, if the exterior boundary is smooth, then U minus U0 will be analytic. So that's going to have exponentially decaying singular values. And you definitely don't want to divide by something that's exponentially decaying. So that's where this regularization comes from for the factorization method. And so all the stuff I've talked about here and what I'll continue to talk about for this problem is in this paper here that was published at the end of last year. And so just what is the analytical framework for this? So I'm just going to assume that I have an operator A. It will map a Hilbert space into its dual space, just like ours does. It maps H1/2 into H minus 1/2. There's some Hilbert pivoting space in the middle. So in our case, that's L2 on the boundary. I'm going to assume it has a symmetric factorization, just like our operator has. And here I say you need to have a complex Hilbert space, but if you don't work in complex Hilbert spaces, this result still works, but you have to add an extra assumption that this bilinear form is symmetric, okay? And I like to think of this as, in all of physics and engineering and things, right? There's conservation of energy, mass, momentum. I think in mathematics, there should be a conservation of assumptions, right? If you want to drop the complexity assumption on your Hilbert space, you have to add an extra assumption somewhere else to get the same result, okay? And so what the result says is that assume that your operator S is compact and injective. We have that for our operator S. Assume that T is strictly coercive, and you only need it to be strictly coercive on the range of S. So not even on the whole space. So it can just be strictly coercive on the range of S. Then you have, the range of S star can be identified with this limit. And so X alpha is the solution, the regularized solution to AX equals L as an operator equation. And so we can show that, it's a regularized solution to this, linear operator with a linear compact operator. So you can write the regularized solution like so. The X's, again, are the singular vectors. The lambdas are the singular values for our operator. And the phi here is just the filter function, and alpha is the regularization parameter. Okay. And so I'll give a little bit of a hint about how the analysis works for this. First thing, you have your operator, and we're going to write it using its singular value decomposition. Okay, so that's not groundbreaking. That compact operators have singular value decompositions. But the nice thing is the left and right singular vectors have this equality, that the dual pairing of X and the singular vector Ln is equal to the inner product of X and Xn. And you can use this to show that they actually, the left and right singular vectors, they are a dual basis to each other. So the Xn's are a basis for X, the Ln's are a basis for the dual space, and they are actually a dual basis. So that's nice because one, you have the standard factorization method gives you this. And using the fact that these are, this property holds and that they form a dual basis to each other, you can show that once I have my regularized solution, if I compute this dual product, I get exactly this here, where phi is my filter function. And we'll give some examples of filter functions and what assumptions are needed in a second. But I have this here. And it's like, oh, these look very similar. And as we all know, the common assumption on filter functions like this is that they should converge to 1 point-wise as alpha goes to 0, right? And so you can then show, under some assumptions on the filter function, that this is finite if and only if this series is finite. And then you just cut out the middleman and say L is in the range of S star if and only if this is a finite quantity, right? And so, just some filter functions that, you probably all know and love are, from Ticknall's regularization and just the spectral cutoff here. And the assumptions that I take are that the filter functions point-wise converge to 1, and that they're uniformly bounded with respect to T and alpha, if alpha is positive. Here, this is a standard assumption. Usually filter functions, this C reg is 1, right? You don't necessarily need it to be 1 in this analysis, but for any standard filter function, C reg is equal to 1. And so we can, rewrite this using a regularized factorization method. Z is in the region of interest if and only if this is a finite quantity, where again, you just have to find the regularized solution to this here. So, okay, let's write this out. Let's specifically say we take Tickner-Hall's regularization. We compute the regularized solution and plug it into this dual product here. Then you actually will get this sum. And what's nice is that this makes sense. Here you have, lambda cubed in the numerator. Here you have lambda to the fourth and an alpha. So at least formally, if you let alpha go to 0, you should get 1 over lambda, which is exactly the form you get from the factorization method. But the nice thing is, this has that 1 over lambda type behavior for small alpha, but you're not dividing specifically by that small number alpha. The small numbers that are the singular values. So rinse and repeat. How do you use this to recover the region? Pick some grid points, compute this. And if you want the boundary, you can either compute the region using the contour plot of this, or if you want the boundary of the region, you can get a level curve. And actually, another thing I want to say is that nicely, I actually don't have to solve right here. You say, oh, I have to find or compute the regularized solution to this problem. You actually never need to do that due to the fact that, well, I'll go up here. It's a little bit simpler. This dual product is always going to be given like so. So if you say, I want to use Tickner-Hall's regularization, you already know what the filter function is. If you already know what the filter function is, you can always just regularize this basically by taking the filter function squared in the numerator. So you actually, at each step, you don't actually have to find the regularized solution. You can just plot this, and that's what I do in my reconstructions. Okay. And so I want to say for some people in the audience, you probably say, this looks very familiar. And that's because this is exactly the result you would get if you use the generalized linear sampling method. And so the idea here is if you take a sequence in your input space and consider this functional here. Now for us, this operator is positive. So we can look at the generalized linear sampling method for this. So if the sequence that you found satisfies this assumption that, it's close to the minimizer of the functional itself, then you get the same exact result, literally the same exact result, okay? And one thing I saw, and I looked at this and I said, this basically just looks like a regularization for this equation. You try to find something that minimizes the residual, and you add in some penalty term. It's just that the penalty term, right? If this was Tickner-Hall, that would be the identity. Here, the penalty term here now depends on your operator. Okay, so this does actually just act like a regularization technique specifically for positive operators, right? And so if you run through this, you can actually compute the minimizers. So the sequence here that will take are the actual minimizers, since we have that positive operator. And so you do the same trick. You compute the minimizers. Once you have that computed, you plug it into this dual product and you get this here. This is the sum that you would get. And you say, oh, okay, well, that just means the filter function for the generalized linear sampling method is given by this. And indeed, it is not a hard exercise to check that if point-wise converges to 1 and is uniformly bounded for alpha positive. So here, the generalized linear sampling method is actually covered by the regularized factorization method, just due to the fact that for a positive operator, that is a legitimate regularizing scheme. And nicely, for positive operators, right, you don't need this assumption because the sequence here that you can, the sequence that you compute here is just the minimizer itself. So you don't need that extra assumption. All right, so that was a lot. So let's get to, I'm sure, this is probably everybody's favorite part of the software. We're going to get through some numerical examples for this problem and also for some other problems. I want to show, this is a very nice general theory that can be applied to different inverse boundary value problems. So we'll see some numerical examples for this problem that we talked about here today, and some other problems, some other applications as well. And so for this problem, just to, the setting, we need the normal derivative of the Green's function. So for simplicity, we're going to take D to be a disk. And that means that the normal derivative for the Green's function, right, we know that from the Poisson kernel formula for the disk. And so you can easily again, compute this mapping where I'm going to take complex exponentials as the Dirichlet data. And I do that because if I use complex exponentials, then the U0 here is quite easy to compute. And instead of solving for U, I solve for U minus U0, and that's going to solve this equation in the region D. Right? Remember, U0 is known because if I know the Dirichlet data is a complex exponential, then this is simple to compute. So now that I have this, you can just use a spectral method like I did to compute U minus U0. And once you have an approximation by the spectral method, you just take the normal derivative with respect to R and set R equal to 1. So for us, our regions are going to be star-like with respect to the origin, just for simplicity. And rho is going to be the function that describes its shape. And so here, this is the first example. So if you look at this kind of pear acorn-shaped region, right? This is the contour plot of the function W using the regularized factorization method. Here, I take alpha to be 10 to the minus 5. So I just took the regularization parameters to be ad hoc. And I'm not sure of what would be a good, kind of discrepancy principle. And that's a very good question to try to answer is what would a discrepancy principle look like for this to pick maybe an optimal alpha. So I do this just, ad hoc, where I just use the spectral cutoff as my filter function. And here delta, I add 5% random noise to the Dirichlet Neumann mapping data. Okay. So you see good one reconstructions here. Once again, this is the contour plot of W, and this is a level curve, which I believe is W is 0.1. Okay. And here, like I said, I wanted the region to be star-like with respect to the origin. So let's take a star-shaped region, and you rinse and repeat. I again use the cutoff, spectral cutoff with alpha equals 10 to the minus 5 and 5% noise added. And here again, the dotted lines on the figures represent the actual boundary that we're interested in. Right? And so, like I said, the regularized factorization method and the generalized linear sample method for this specific problem for positive operators, they're one and the same, just because that functional that you use there defines a regularization scheme in kind of the traditional sense. So I do the same exact thing. I take alpha to be 10 to the minus 5. And I say, well, if I use the filter function for the generalized linear sampling method or for the regularized factorization method, I should get the same thing, right? So I do this for this kind of rounded square, right? So here, this is what the generalized linear sampling methods filter function, and this is with the spectral cutoff filter function. Okay. And so what I want to say now is, just like the factorization method itself, this can be applied to many different inverse boundary value problems where you want to do some kind of shape reconstruction, right? And so this is a problem that was working on with a graduate student here at Purdue. And so we are looking at, so this is an electrical impedance tomography problem. And the idea here is the region of interest that you want to recover is D. That's in some subset omega, where U is harmonic everywhere except for the boundary of D. You have the prescribed, here the prescribed voltage on the boundary. And there's a jump in the current across D here. And so this models some type of corrosion here. And what the graduate student was able to do, he was able to work out not only the regularized factorization method, so it works for this problem as well, but also they were able to come up with a nice asymptotic formula for small volume regions. And then you can also use the kind of a music type algorithm to recover if you have multiple small type regions. So we have that in this paper that was just submitted. And here I give, this, I can't remember what filter function this is using. It might be Ticknall-Hall's. This is taken more or less directly from the paper, so you can check it. But second verse, same as the first. We applied the regularized factorization method. Here is the contour plot. We're just recovering a circular region here. And here is the level curve where the W here is 0.1, okay? So that's a problem, right? So we looked at, basically diffuse optical tomography. We've seen it here used in electrical impedance tomography and in scattering as well. And so what I looked at here is that you can, can apply this to problems in inverse scattering. So in this paper that was submitted, or not just submitted, but submitted, I looked at applying this for near and far field measurements when it comes from inverse scattering. And here, I'm just going to talk about the case for far field measurements. And the idea here is for the scattering problem, the region of interest is some region D, that's a subset of free space. Your scattered field is an H1 Lok solution to this kind of modified Helmholtz equation. And so Q is the contrast. So if you think of this in terms of acoustics, you can think of that the sound speed, we kind of normalize things to be 1, let's say, outside of the object. But inside the object, the sound speed is different, and that's modeled by this Q here. So Q has compact support. The support is the region D. That's the support of the contrast. So you want to recover not the function Q. That's not what we're recovering. We're recovering its support. So we're recovering the region D here, okay? And for the case where you use far field measurements, the input that you have is a plane wave. So K is your wave number, and this Y hat is just the direction that the incident wave propagates. So pick your favorite point on the unit circle or sphere, and then you can send in an incident wave all around them. And so here is a reconstruction from this paper. And what I have here is, you might ask yourself, why? Does this actually help? Does regularizing the factorization method, is it needed? Or is this just some academic exercise? I say, probably everything that I do is an academic exercise, but this might be an academic exercise that might be useful. And so here I reconstruct this kind of, this is not a star, what is it? Flower-shaped region. And so here, this is with the factorization method with no regularization. So the filter function is not added to that sum. I plotted just like we talked about. And we see here, you miss out on actually, it knows that something is there, but the numerical instabilities, because I add here 10% noise to the far field data, don't allow you to recover the shape very well. Whereas if I add in some regularization, right, so alpha not being 0, you can recover the region quite well, okay? And so I will say, this is, the idea of regularizing the factorization method was done in some previous works, but the thing I did here was basically prove that it will work, right? When you do this, as you let alpha go to 0, you basically recover the result from the factorization method. So this regularization is valid, and we see it is actually needed in some cases, that when you add enough noise, right? So here, if I add less noise or no noise, then these pictures with and without regularization, they're indistinguishable in the eyeball norm. But as soon as you add a significant amount of noise, then you can see here, there might be some numerical instabilities from dividing by those singular values. And so those are some kind of current works. And here, ongoing thing that I'm looking at, and I kind of think I know how it should work out, is what happens if you perturb the operator. So here I added noise to the operators in all of these examples, but I don't have the theory yet that says what happens if you add noise and basically you let the noise go to 0, right? So the next question is, if you were to have, more or less the same setup for a perturbed operator, such that, the perturbation goes to the perturbed operator converges to the operator as delta goes to 0, then what I believe we can show is this result. So now you have to take a double limit, let alpha go to 0, first let delta go to 0, then let alpha go to 0. And then you should recover the same exact result, where this x alpha delta is the regularized solution to this problem here now. Okay. And it is important that you take the delta limit first and then the alpha limit. But I think I know how to do this, and that's something I'm looking at, trying to finish that up. And it uses a lot of techniques. Armin like to looked at something similar to this for impedance tomography. Specifically, the perturbation he was looking at was a projection, where you don't have the full Dirichlet and Neumann mapping in any calculations that you do in real life. So he said, well, what if the perturbation was just a projection? So you have, instead of having the actual Dirichlet and Neumann map, you have a projection onto some subspace. And he was able to show something like this. So I think the same kind of a lot of perturbation theory and things like that can work out to prove this result here. Okay. And that's all, folks.
Thank you very much, Isaac, for the very nice talk. Thank you very much. Are there any questions or comments, please?
So this is Margaret.
Hello.
I'm wondering, about the same thing I'm always wondering about is like, can we apply this method to radar? And so the problem always is with radar, what you naturally have is time domain data and a very limited aperture. Do you think any of these techniques might apply to that problem?
That's a good question. So normally when you have the limited aperture, from my understanding, a lot of times the limited aperture means you don't have the symmetric factorization that's necessary here, right? So a lot of times you will have a factorization like this, but you have the S here, but this necessarily won't be S star, right? And so I think it can kind of depend on, you could probably get the symmetric factorization if your sources and receivers were on the same curve. So this is a problem when maybe your sources are on one part of the boundary and your receivers are on the other part. Then this is S, but this is not S star here. But I think if you have your sources and receivers at the same place, you may be able to get away with something. This, you have your operator S. This may be S star. You could probably run through something similar. But I think I know for some limited aperture problems, that is a big failing in the factorization method, that everything hinges on the symmetric factorization. And sometimes you don't have that, especially, like I said, when the sources and receivers aren't at the same locations.
Yeah, and in radar, often what you have is just backscattering data. So you're transmitting and receiving on the same sensor, but then that sensor moves around, and so you get different views. Yeah. So anyway, if you have any ideas, that this has been a problem that's been around for a long time, and we're all hoping to be able to solve it someday.
Yeah. Yeah, thank you. Thank you for the question.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Okay, if not, thank you very much, Isaac, for the very, very nice talk. Thank you very much, everyone, for coming. Thank you.
Yes,
yeah,
thanks
very
for the
nice talk.
Thanks for coming. Appreciate it.
Thank you.